other than personal delivery.
I don't remember, where did this chart come from? What year was it developed with?
It was developed mathematically by Dr. David Cockrell from the University of Leicester in England. It is part of the Air Force and Navy's Recovery System Design Guide.
Was it developed theoretically, or was it developed based upon test data with particular types of...
My understanding, it was based on years of experimental test data by the military.
Okay.
Okay?
So it was probably developed with round canopies, maybe C9s or something.
Yes, but remember what we're looking at here. We're not looking at the actual inflation. We're only looking at the peak load, which occurs at snatch.
Okay, at the snatch force?
It is the maximum opening force calculation. If it's infinite mass, that means there's no diaper, so you get a canopy first. And yes, the answer is it is snatch force. The hardest part of any opening should be snatch. Should be. That's if it's in order. Yeah. Okay? In an infinite mass, which we're going to get into in a minute, and let me finish this and go to CX and you'll see it better. But the point I want to make about the X1 factor is it has revealed something to me that the industry had never considered. Weight doesn't mean shit on hard openings. If you double the weight, you will increase the force or the resultant of this formula by 1/10. In other words, if you double the weight, you will increase the opening shock by only 10%. Used to be, when we'd sit in the TSO committees, we'd say, oh, if you can't go fast enough, just add weight. So when I did the tests, the original tests on the SST, we used a Navy conical, no diaper, canopy first, infinite mass deployment in a twin beach with 300 pounds. We started with 250, we went to 300, we got no change. We weren't reaching 5,000 pounds. So we went up to 350. We still didn't, minor change. We could barely measure it. We were using a peak meter, which only measures 1 point, and that's the highest point that we hit. We finally took it up to 200 miles an hour. We dove that twin beach at the ground and got 200 miles an hour out of it and kicked that load out, and it was like a 155 howitzer going off. It's just, a 5,000 pound opening shock is the most horrendous thing I've ever seen in my life. I've done a lot of testing in this world, and now we've got weight and speed categories. You don't see 5,000. You don't see anywhere near 5,000. 3,000, 4,000 pound loads, most you ever see in a high-end, really hard structural test using weight and speed parameters, which I don't think are sufficient. Okay, X1 factor has taught us that one thing. Double the weight, and that, I want to make the point that that's counterintuitive to skydivers, because we all think, oh, you're fatter, you fall faster. Well, that may be true, but suppose you get a bigger jumpsuit. Okay? So now we're not falling faster, but we weigh more. And that's where you have to consider the problem, because speed is considered separately from weight. So the phenomena of increasing speed by weight has to be taken into account over in the speed area, the dynamic pressure area, not in the pound per square foot loading area. Okay, go on. The shock load coefficient. Now this is another page extracted out of the design guide, recovery system design guide, excuse me, from Konecki's book. Now one thing, I put this up here, notice it says infinite mass, okay? Opening force coefficient, or CX. This is the line we're interested in. This happened to be solid textile parachutes, flat circulars, conicals, biconicals, triconicals or polyconicals, extended skirts or T10s. It talks about the diameter, the shape, the inflated shape, the drag coefficient, the range of the canopy. And we're going to tell a story here in a minute about a conical. And we want you to note that the opening force coefficient, the CX, is 1.8 for the conical. Okay? That's infinite mass. Now once again, infinite mass is no diaper, no deployment first. It's canopy first. That canopy comes out and opens and you come to the end of the lines. That's infinite mass. We don't know how much mass that canopy is, so it's called infinite. If the canopy stays closed and is in a bag or a diaper configuration, that's finite mass. The CX would change. Okay, opening shock formula, we've now finished it. Force, CDSOQ, the old drag formula, plus the X1 and the CX. The CX can only be determined by testing and measuring. Oh God, I had some people say, oh, I tried to use that formula and I can't use it. Well, it's not to be used right off the top of your head unless you've got some data validate what you're doing. It accounts for such thing, the CX accounts for such thing as slider size, trim angle, nose angle, weight, deployment sequence, etc. In other words, it's a catch-all for the design of the package, which includes the canopy and the deployment device. Once the CX is determined, the other variables may be exercised to predict how this design might perform under those conditions. That's what we use it for. You go out, you test the design, you get the numbers, and then you can extrapolate other changes in other environments and get information. Now we're going to talk about the phantom in the air and the significance of the CX. Phil may probably remember this. Maybe about 20, 30 years ago, there was an air show in New Jersey, and an aerobatic pilot was flying a Yak, a Russian low-wing aerobatic aircraft. He put in a high-speed dive, the wing came off, and he got out and fired his 5,000-pound certified emergency parachute. And first time I heard about the story, they said he pulled with his seatbelt still on, and I got thinking, well, 5,000-pound canopy, that sure left his lap in the plane. He came apart, but he didn't come apart. He did bounce. The parachute came apart. The line separated from the canopy. Okay, now why? NTSB goes up and they see the parachute in shambles, the guy's dead, and they say, well, what are the operation limitations on this parachute? Why isn't it placarded? And the FAA, this is back in the 60s, the FAA went, I don't know. They didn't have a clue. NTSB didn't have a clue. Parachuting industry didn't have a clue because we didn't have one back then. We had a few military people, and they didn't know anything about they knew a lot about parachutes, let me tell you. They really did their homework. The military establishment that created parachutes back in the 40s and 50s did a hell of a job. I've studied all their work. The work of David Gold, phenomenal. I had the pleasure of sitting next to him in those aerodynamic decelerator system classes. He's a guy that invented the Navy conical. He told me the whole story about the vent cap on it, but some of those guys were brilliant people. Anyway, the manufacturer of that emergency parachute, I later had a conversation with, and I asked him, what weight and speed did you test that canopy at? At system at. He said, well, I don't remember. He said, we hired a consultant. I went, oh, really? Well, at that time, it was when we were having the AIA conferences, and the only consultant out there that I knew of was Theo Konecki, and I'm sure that the consultant they hired was Theo. And like I say, I've got 80 hours of class under this guy, and I know how he thinks. Theo has never seen a diaper. He didn't know about finite mass deployments. He didn't know we were there. He made calculations using the only published CX for a conical that he could get, and that was that 1.8 we saw in the previous slide. How do I know that? Because to this day, there is no published CX for a finite mass conical. My own personal testing and experience, and some guy that was in this class the first time I gave it, confirmed it, sat over there and said, right on. As a diaper, effectively reduces your opening shock by about 50%. So we looked at 40 to 60% change, giving it room for variable. So that means if Theo calculated this thing and using a 1.8 and he came up with weight and speeds, and they tested it with a diaper, and the weights and speeds were without a diaper, that means that a canopy that was supposed to be 5,000 pounds strong was only maybe 2,400 pounds strong. An interesting point, we're talking about phantoms now. I carried a Phantom on my back for years. The Phantom 22 never passed standard category. It only passed low speed category. They couldn't make it pass. I think the reason is, like we're saying, it just wouldn't take it. A little canopy opens a little harder. That canopy never saw, in my mind, more than 1,500 pounds test load. And what's interesting about that is that canopy, in the sport use, never failed. Never had a problem. So that made me feel good. 1,500 pounds is a...
The doubling of the bands and other things of this nature, the tightening of the diaper, didn't that come out of problems were found?
That was the result of a misdiagnosis of this whole problem. Yes, they never understood the root cause of their problem, that their canopy was never properly tested, and yes, they came out with the diaper and the Kevlar bands, which was basically a hand wave and didn't help a thing.
Was that a result of the accident that you're discussing? Or
Yes.
was that a result of failures in the skiving community? Because I thought people
Failures where?
in the skiving community. I heard stories of people split doors in the skiving community.
In the skiving?
Skydiving.
Oh, okay. I never heard about a split door.
Okay.
The actions those actions of Kevlar and the diaper tightening and what have you were as a result of the yak failure.
You're saying 20 or 30 years ago when this happened. Has there been another one more recently? Because I talked to an FAA guy and he was talking to me about something about 10 years ago.
Well, there may be. I'm not familiar with it. I can't attest to it. I've actually just come to the realization of Konecki's thinking and his understanding and what he possibly could have done, and the fact that that CX was not ever published, and it led me to this conclusion, and I'm sure it's a correct conclusion at this point in time. And it was a misunderstanding. So as a result of this screw-up, the FAA couldn't. So NTSB saying, why isn't it placarded? The FAA said, we don't know. And so the movement began about placarding everything and putting a weight and speed on it. We're going to go into that right now. First of all, we got one other area to cover. Testing was required by ACOs. ACO is the Aircraft Certification Office. Here I'm worried about getting behind. I'm so far ahead I can't see straight. I'll slow down again. Testing was required by different ACOs. Boston required Pioneer to test and measure all of their opening shocks, and Pioneer did a very clever thing. They had a mechanical device which had like a valve inside of it, and it would pull up like this and hit, and it was a point that it would hit on a clean plate of metal, and that's called Brunelling, and it's the same basic principle as a Rockwell hardness test, and you can measure the depth of that hole and see what the opening shock was. Brilliant! Jim Roeder showed me that, and I went, wow, what a neat thing. I called Chicago, my aircraft certification office, and I said, I want to test parachute harness container, and what are your requirements? He says, well, what are you going to test it to? And I said, 5,000 pounds. They said, prove it. Measure it. So I went in the automotive industry digging for data. This is before we had data loggers, data acquisition systems. The beautiful systems we have today are fabulous, but back then, I went to these guys and I didn't have a clue what a peak meter was, but if you think about it, it's a box about this big. I've still got it. It's got a capacitor in it, and it reads one voltage point. A Wheatstone bridge or a transducer, force transducer, has got a balanced Wheatstone bridge in it. You excite it with voltage, and you read the output voltage and measure the differential. And what this peak meter did was it read that, but it only recorded the single highest point. So when I went to the TSO committee meeting, I got challenged initially because I said, you've got to measure it. And they said, you can't measure it. I said, use a data logger. And I didn't realize how lucky I was to get the advice to get the single point. Because the first thing the rest of the industry did was they came down on my head and said, you probably missed a peak point. If you're not what rate are you recording at? 200 readings per second, 200 samples per second? No, I'm only recording at one sample, the whole thing. So I can't be missing a peak. And boy, were they disappointed. Their faces dropped. I like Pushkas. I remember the look on his face. Oh. And they TSO'd the...
How exactly did that device work? Was it an analog device which would measure the peak, or was it...
Yeah,
okay.
an analog device that remembered the highest peak voltage with the capacitor. Really simple thing, but it was a break for me because I had an argument that I measured mine, and they said, well, we can't measure. And I said, hogwash, you can measure. They talked to New Jersey ACO, both national and Paraflight. Unfortunately, Paraflight's Safety Flyer, the first ram air parachute, when they first started building ram air parachutes, those things were Iron Maidens. They were really overbuilt, really strong. Fortunate for Paraflight, they talked the FAA into certifying them using a weight and speed off of the table in TSOC 23B. There's a weight and speed table, which we're going to talk about a whole bunch in just a minute. And they talked the FAA into using that table. So did Ted Strong when he TSO'd his LOPO. Now, once again, Ted's LOPO was a really strong canopy. The safety flare was strong. But that Phantom was a little bit flimsy, and it always worried me, but I thought, oh, I like lights, you know, and I was the same way. Okay, so New Jersey and Atlanta areas allowed charts and calculations. All right, test standards. NAS 804, which is TSOC 23B, which is the old standard that was written back in the 40s and that all the rest of the people in the industry hate, and I don't. It had two categories, low speed and standard category. Why do they call it high speed? Anybody know? Okay.
Sounds better.
Okay, anybody here on an airplane, private airplane? Okay, what do you got?
I used to have an old Cessna 150.
What category was it in?
I forget, I think it was called a utility.
Exactly, utility category. And a utility category is limited to pitch and yaw,
Yeah.
pitch and roll.
And you could spin it, but that was it.
Yeah. The next category up includes aerobatic, crop dusting, and everything else I can imagine. It's called the standard category. It has no limitations. FAA thinking in the 40s, standard category, no limitations, unlimited, tested to 5,000 pounds. What that means is if you exceed 5,000 pounds, you won't need the harness. You know, Mike Furry said it best, you should be separating body parts before harnesses come apart. At 5,000 pounds, that's exactly what will happen. We already know that even at loads lower than that, we killed about 20 people in this sport with broken necks from line dump, hard opening, line dump. And Mr. Getch, almost, we're fortunate to have him with us. I've seen the x-rays of his neck. He had a really ball-busting, neck-breaking opening. He's lucky to be alive, quite frankly, and he knows it. And that was about 15, 20 years ago, I guess. I'd forgotten about that, Phil. I got some of them in my lower back now, but my neck, they never could fix it. Anyway, so now we know, or have a clue as to standard category. But in that NAS 804, the FAA, in its infinite wisdom, was trying to help our sport, or not our sport, but help the industry, because we didn't have a sport when this happened. They put in a table of weights and speeds for 3,000 and 5,000 pounds. Underneath the table, in little bitty letters, is a statement that says this table was for a 28-foot C-9 Air Force canopy. Now that's all of that caveat that translated into Pointer's manual. If you see the chart in Pointer's manual, you'll see that much under it. But the caveat went on to say, it is presented here for example only. So PIA rewrote AC 105-2. And for compatibility, for TSOC 23B, they tried to use this chart, and they submitted it to the FAA to use this chart as the limiting factors for products TSO'd in that category, which would have included my product. It would have taken my unlimited parachute system and put a limitation on it. And it certainly was not legitimate, and they made a whole bunch of other things. They submitted it to the FAA, and I wrote a letter to the FAA pointing out this fact. And the FAA came back and said, do you have language? And I said, sure. So all of the language that you see in AC 105-2D, the current standard, which we're going to go to in just a second, about compatibility is my fault. PIA went ballistic. They wrote a letter to the FAA and said, this is the worst thing that's ever happened. It's terrible. Those parachutes in TSOC 23C, we don't know what they were tested at, which is just not true. In some cases it is true, but not across the board. So they demanded a reshot. So the FAA says, resubmit, we'll look at it again. So they resubmitted AC 105-2E a year ago. They submitted the same document that the FAA had already rejected and revised. What is it they say stupid is? Doing the same thing twice, expecting a different outcome the second time.
But they are dealing with the FAA.
FAA is a whole lot smarter than anybody gives them credit for. They really are. They're a very good organization that is hands-off unless they have to be hands-on. I have infinite respect to the FAA and what they do. I wish they would do more in our sport. But I defend their methods, and in a capitalistic free society, those people do a fabulous job, I think. They have helped me every step of the way through this 50-year odyssey of mine, and I'm a fan of the FAA. Certainly we run into some that are really idiots, but we can handle them.
People that are not dealing with parachutes.
Pardon?
People that are not dealing with parachutes.
Yeah, they're not familiar.
Now, I've been lucky, because I've never had that experience like that, but there are plenty of stories about it.
Oh, yeah. But I find that most of the stories usually have two sides. They really do. Anyway, so we're going to 8015A, 3 categories at 300 pounds. That 230-pound category was insisted upon by the FAA. We originally wrote the standard for the 130 and the 175. The FAA came back and said, we got to have something unlimited, something big for 747 test pilots. And to me, that memory was a clue about how the FAA was thinking about this whole thing. Okay, so what's the difference? Structural tests of NAS 804 were strength tests, 5,000, 3,000. The structural tests for 8015 and its subsequent members were for weight and speed without regard to force, no measurement required. Why? You got to understand why the industry wanted that. Boy, we're getting sleepy around here, but we'll go faster. Hey, everybody wake up. I'm yawning too. It's oxygen deprivation. We all know that. As skydivers, it's not that we're sleepy, we're just at too high. That's one right. Anyway, weight and speed without regard to force, no measurement requirement. There's a reason for the industry wanting this. Measurement is a bitch. Measuring a parachute opening shock, especially on a high-speed drop test. I used to think if I got 30% data, if 30% of my tests produced data, I was doing pretty good. We've worked over the years to improve our data acquisition system, and we pretty much get data every time now. But I know and have great sympathy for the other manufacturers. Getting data on a structural test is a bitch. Measurement of parachute forces is a bitch. Now, things have improved, we got better data loggers and what have you, and we're doing better. So anyway, they have this weight and speed with no regard for force, no measurement required. That's not a bad thing if all you're going to TSO is a single parachute. Here's a parachute, harness, container, canopies, it's TSO'd, you can't change it, it's the way it is. Well, if you have a parachute which is TSO'd under C23C, that's the way it is. There is no metric by which you can cross-compare the canopy to the harness. Now here's your example. Remember the CX that we talked about? The CX tells the story of the canopy. So manufacturer A over here, really sharp guy, makes a canopy that has a very soft opening. Maybe 1,500-pound opening at the highest weights and speeds. Suppose they're going to TSO it for 300 pounds because the margin now is 1.2 times the placarded, and that's grossly inadequate, by the way. 1.2 times the placarded weight and speed. So we test it at, say, 300 pounds, 150 knots, and we get a 1,000-pound opening shock. Well, we don't measure 1,000 pounds, but that's what it generates. So company B over here goes out and they do the same thing. They build a system, but his system opens really hard, and he has to build a super strong harness for it. Okay? He goes out and tests it at the same weight and speed, and it drives a 3,000-pound opening shock out there. So now it comes to the field, and rigger wants to take this canopy and put it in this container, and wait a minute, you've got a canopy out here that opens like a ton of shit, and a harness over here. It was designed for a soft opening canopy. It may not take the stress. They reach that far. So you can't do that. Weight and speed does not give you a metric by which you can make a determination of structural compatibility. So as a result, when we wrote TSOC 23D AS 8015C, we put in there the necessity of the manufacturers to placard the force generated by the weight and speed that they're placarding at. So that now the rigger in the field has a metric by which he can compare. The harness makers also have to provide what force their harness has been tested to. So we've got a placard for weight and speed for the woofs that want and needed weight and speed, and we've got a metric now to provide cross-compatibility. Why doesn't it? Every design is different. I've actually talked about this, but I'm going to read the slide just so I don't miss any points. Every design must have its own CX, which is a major descriptor of how hard a softer parachute opens. AS 8015B, or in a little sub-X, that means subsequent revisions, have forced placard requirements. The canopy, which tells how strong the canopy is and what it will generate at the weight and speed for which it is placarded, and the harness container, which tells what the load the harness has been tested and is certified. The harness must be equal to or greater than the canopy. The speed is limited. The system is limited by the canopy weight and speed. Oh, and we all know the big flaw in TSOC 23B and AS 804 with the 3,000 and 5,000 pound category. You could take a low-speed canopy and put it in a high or standard category container, and you didn't have to re-placard it. The FAA never made that regulation, and they should have. But it never caused a problem in the sport because standard category was just a plus. Pardon?
That did knock the certified down to a
3,000 pound, yeah. If you put a low-speed canopy in a standard category harness, it takes the system down to whatever the weakest link is. Okay. All right, the canopy speed limit is for force reasons on the weight, and the weight limit is for rate of descent. Remember we talked about the X1 factor, double the weight, increase the opening shock 10%. Really, when we're looking at weight and speed as a descriptor of the capability of the system, the weight is only there for purposes of rate of descent. Okay? Because of the insignificance of the weight factor in the opening shock. So the weight has limited effect on opening force. Double the weight, increase the force by 10%, as we know. All right, now, this is a reprint, extraction of the current language in AC 105-2D, which says exactly what we have just said. It also goes down here in paragraph C. TSOC 23 components may only be used in situations where they're mated with the same components by which they were originally certified unless they are retro-placarded by a service bulletin or other notification identifying the maximum forces generated during testing. These forces could then be applied as in TSOC 23, and that's a typo, that should be D. D components can be mixed and matched with other D components by comparing forces, placarding, certifying weight and speed. Up here we talk about TSOC 23B, low speed, and then we talk about, and by the way, paragraph A here says, in the case of the harness certified under TSOC 23B standard category, the canopy the system is limited to performance limitations. It may be determined by comparing the placard force generated to the canopy and 5,000 of the harness. If the canopy is placarded at or above the 5,000 pound level, the system is considered unlimited. That is validation of what I have just told you by the FAA. We had this conversation in writing with the FAA, and the FAA adopted it, agreed with it, and put it in their document. So what I'm saying about the standard category has been validated by the people that need to validate it. Okay, in the future, the reserve function compatibility issue must be handled by the rigging community and through AC 105 revisions. That's us. And we probably can get AC 105 revisions if necessary. AC 105 should require placarding of pilot chute effective square feet. Like I say, we're already doing that. And providing maximum allowable extraction force in the container manual. Again, we do that. We have published, it's not in the manual at this point, I don't believe, but it is on our website, published. This would be voluntary for the manufacturers if they wished compatibility considerations. It's up to you guys. You can say, I don't think these guys are compatible. There may be a fight with your customers, but your customer's going to appreciate your concern. They put a lot of trust in our rigging community, and rightfully so, because we've got a good rigging community. What do we do now? For now, we measure the extraction force when we get a rig in for inspection. If it's high, we measure it again after we pack it. If it's still high, we refer the matter to the manufacturer. He'll say send it back. Don't. Make that manufacturer tell you what the maximum allowable extraction force is. This kid in England had waited 2 years to get a report back from Sunpath on that Javelin Odyssey, where they said that 32 pounds was acceptable, but on the high side. 2 years. But that's progress, though, you know? That's progress. I'm glad that happened. I don't want to, to diss them for doing that. I think it's brave of them to step out there. They've got to learn a little more about what they're doing and do a better job, but at least they're stepping into the breach. Kudos, Dave Singer. Make the manufacturer tell you what the maximum allowable extraction force is. That's something we can start pushing hard on, and we should. And the British are doing it. The British are doing it in writing. The pilot chute drag capability dictates what the extraction limit is allowed to be. They should know that, but they don't. And that's a scary thing to me. I sat in the tech committee the other day, back in August, and I said, we actually need to know this because we might be changing pilot chutes from one rig to another. And some manufacturer says, oh, that'll never happen. And some rigger says, I did it last week. In the same room. So obviously, this gives us the ability now to swap pilot chutes if one will work in place of the other, like a Javelin and a Wings or a Dolphin or something like that. Don't allow anybody to find your name on a reserve activated by an AAD that's unopened. Let's stop this. It's up to us. We can stop it. All we've got to do is have the gonads to stand up to the manufacturers. And this one rigger I told about earlier who'd done all the testing in Europe and knows, he won't come public. He won't go public with his and let anybody know who he is. He's revealed himself to me, and he's revealed himself to the British Parachute Association because he trusts them. He's afraid of losing his job. He's afraid that the drop zone owner who has relationships with these manufacturers, which are deep financial relationships, he'll lose his job. And I don't know how he's handling it personally, but I know that he's got a lot of agony over it, and he's working hard to try to make it better without putting himself in a bad light with his employer. What do manufacturers need to do? God, a whole bunch. All pilot chutes must be tested and their effective square footage documented and placarded. Testing could be done with a PIA-funded, rigger-operated whirl tower. God, wouldn't that be fun to have? You know, I don't need it. I don't want it. I'm not going to have any part of it. I'll be long dead before it ever gets built, probably. But I think you can do it for $10,000, and I've given Cliff and David a paper explaining how I'd approach it. All containers must be identified as to the maximum allowable extraction force. Damn it, that ought to be done right now, and that's why I'm saying 18 pounds is a working number for you guys. But most of those pilot chutes won't pull 18 pounds. Matter of fact, 18 pounds is a lie that we use in our ad. It's a lie because I ran the numbers, and the numbers are 17.92 pounds at 1 second after cutaway, the Q of 3.03, I think. So we lied a little bit, multi-fraction of a second to get to 18 pounds, but it was only 17.92, and that was with a racer pilot chute, which has 5.92 effective square feet. If you've got a pilot chute that has 2.3 effective square feet, 18 pounds, it ain't never going to pull it out of there. So you've got to drop that number down. How much? Well, in the case of that one pilot chute that I happen to have tested at NASA, I could do the numbers and calculate it, and it'd be down around 10 pounds or something. I'm not going to do it now, but those are things that you guys have got to be aware of and have to keep the pressure on the manufacturers to get these pilot chutes graded. That's what I call it. Anyway, this will give riggers the tools to make good decisions about functional compatibility. And one more thing. Okay, we'll do this first. PI needs to revise TS-135 to revise structural standards to a force standard from this weight and speed thing so that we've got a metric. Conduct structural testings of load-bearing components without attenuation devices. We put an attenuation device on, we want to test structurally, we've got to get up to the 200-mile-an-hour range. Take the attenuation device off, we can do it at 100 miles an hour. And we can measure the strength of the structural components at a low speed, much easier to do. Of course, that would increase the competition in the minds of some of the manufacturers, and they've been opposed to it. They won't even, every time I've tried to present that idea, they've talked me down, shouted me down, as a matter of fact. Conduct the structural testing of load-bearing components without the attenuation devices. No bag, no pilot chute, just throw it out and measure it. And you can tell how strong a harness the canopy is in that. Measure to a prescribed force level with force measurement to provide proof. Require pilot chute testing and placarding. Require identification of mass extraction force. That's what PIA needs to do. Now, you're a rigger in the field. You have the right to test. Okay? You don't need a dummy to test a parachute. You don't need anything but the parachute. If you were to have the need to prove the function of a reserve system, simply fasten the leg straps and stow the ends like you were wearing it. Put the chest strap through the leg straps and fasten the chest strap. Make sure nothing is loose that might flap in the breeze, because it will when you throw it out from an altitude high enough to activate the AAD. If it opens at 750 feet or so, we have a winner. No damage, no problem. If it doesn't open, call the manufacturer, get an RMA. You don't want it back anyway. Tell them to just send you a check. And I'm serious about that test. I'm hoping that we get to conduct that test on those stuff from over there. I don't know if we'll get the opportunity or not. There is my new favorite drawing. That is an AutoCAD 3D drawing. I wish I could rotate it for you. Of our newest canopy that we're going to call the Mentor 9. And I'm so proud of the drawing. I got 100 hours in it. It's a new concept. It's an enhanced arc anhedral with compensated line lengths. And you can even see the risers and toggles. I stuck it in there just as kind of a...
Define this arc anhedral.
Huh?
Define what you just said.
Arc anhedral. The arc anhedral of the canopy is the wings have dihedrals. Ram airs, parachutes have arc anhedrals. And the anhedral is, it increases stability. When we first started making ram airs, we adjusted lines to keep them flat, and they would turn, they would fold up and turn. So that arc anhedral, if the line lengths aren't correct, you get a lot of wrinkles in your skins. Okay? And so the lines have to be set up properly to keep the skins from wrinkling.
You try and turn this into a single arc as opposed to two arcs like that?
No. And yes and no. But I'm trying to control the arc to keep the skins tight. It's maybe what I'm trying to say to you. If you look at my canopies, you'll see there are very few wrinkles in them. And it's because they're all 3D CAD designed. And the lines are now, this new process, I apply the lines after I draw the arc. And I have the ability to take and move the jumper up into it. And what I've done here is I've got it up a little tight, intentionally. You can see that's pretty short distance. And the reason for that is this is supposed to be a student canopy. And I think it may be an accuracy canopy. If you're down here and you do a turn, you're going to do a carved turn. But if you're up here and you do a turn, you're going to be more tendency to stay coupled.
Okay, so it's going to be a student canopy, but it's going to be more responsive because of the short alignment.
I think so. I'm hoping so. We got one jump on it so far, but I like the drawing, so I thought I'd share it with you. Okay, that completes my presentation. I would entertain any question. See, I did a 2-hour class in an hour. That's because you guys listen so well.